we finished the discussion on equations of motion of multi-degree of freedom systems, and now we'll study the free vibration. So, free vibration analysis of multi-degree of freedom systems. Now, to keep the presentation simple, we'll work with 2 degrees of freedom system, but all the conclusions can be extrapolated easily to systems with n degrees of freedom. So I'll write here free vibration analysis of 2 degree of freedom systems, but it is understood that everything applies to systems with n degrees of freedom where n is arbitrary. Okay, so when we talk about free vibration analysis, forces are 0. So F, the right-hand side in the equation of motion is 0. Is equal to 0. And we'll consider also that there is no damping. So consider no damping. Okay, so the equation of motion contains only the inertia terms, mass times the acceleration, and the stiffness terms, which is the stiffness matrix times the displacement. So the equation of motion that we'll solve is this. This is the equation of motion. So we have the first, the mass matrix times the matrix of the acceleration plus the stiffness matrix times the vector of the displacements equal to 0. That's the equation that we have to solve to find the free vibration. Or you can write it in a simpler form, more compact form, mass matrix times the vector of accelerations plus stiffness matrix times the vector of the displacements is 0. Okay. In general, if you have a problem like this, the solution is an exponential function. Okay, why is that? Because if you take the derivative of an exponential function or the second derivative, then you still end up with an exponential function. And you can adjust the coefficients so that this equation is satisfied. That means the inertia term plus the stiffness term add up to 0. So we consider that the displacement vector, which consists of the 2 displacements of the masses, is equal to a vector with 2 constants, 2 coefficients times E j omega t. Okay? Now, be careful here. You may wonder, the displacement is something real that I can measure. Why we are writing here complex? Well, it is implied that we consider the real part of the complex number. So this is implied, but will not be repeated, okay? So will be omitted from the notation. So a real part of the right-hand side is considered. Okay. But for compactness, we don't write it. Okay. So what we need to do now, if we make this assumption, is to take the derivative, the second derivative, plug into this equation and see what we find for the displacements. Okay, so we have made an assumption about the displacements. This is the assumption. And then we'll take the second derivatives and then plug them into this equation of motion. Okay, if you take second derivatives, then you will have minus omega squared. You will have j omega times j omega, which gives minus omega squared, times this vector with these two coefficients, times ej omega t. Okay. If you put these two expressions in the equation of motion, then you get this equation. Stiffness matrix minus omega squared times the mass matrix times the vector of these two coefficients is equal to 0. Okay? This is an equation that has an obvious solution if you are looking for A and B, the two displacements, A and B. What is this? Well, if A and B are both 0, the equation is satisfied. But that's a trivial solution, which essentially corresponds to the fact that the two masses don't move. Okay? Besides that, there are other solutions, and this is what we're trying to find. If you want to find a non-trivial solution, it can be found if you consider that the displacement, the determinant of this matrix is 0. So we have a non-trivial solution if the determinant of this matrix is 0. Non-trivial solution if the determinant of k minus omega squared times m is equal to 0. Okay. This is an equation with respect to omega. So you can solve this equation for omega to find the frequencies of vibration of the two masses. This is called characteristic equation. Okay, going back to this equation, if you multiply by the inverse of the mass matrix, then you have another equation which is m into the minus 1, the inverse of the mass matrix, times the stiffness matrix, K, times AB, the matrix of the displacements, equal to omega squared times AB. Okay. Now, what this means is, if we remember eigenvalue problems in linear algebra, that means that omega squared is an eigenvalue of this matrix, and AB, this vector, is the eigenvector. So here is the conclusion. Omega squared is an eigenvalue of this matrix. Now, because we have 2 by 2 matrices, we have 2 eigenvalues. So omega squared are eigenvalues of matrix M into the minus 1 times K. Okay, and AB, this vector, contains the eigenvectors. Okay, in the language of structural dynamics or mechanical vibrations, we call omega the natural frequency. And because we don't have one solution, we have actually 2 solutions, omega squared omega is called natural frequencies. Natural frequency. Okay, now if we write this equation, this is an equation with, I'm sorry, this one. This is an equation for omega. Then you get a 4th order equation, 4th degree algebraic equation. So if this is, say, the characteristic equation, from the characteristic equation, you get this algebraic equation, which is a 4th degree equation. M11 times M22 minus M12 squared times the 4th power of the natural frequency minus M11 K2 plus K11 times M22 minus 2 times M12 K12 omega squared plus K11 K22 minus K12 squared is equal to 0. Okay, this is a 4th degree algebraic equation. There is a closed form expression for the solutions. There are 4 solutions in general, but if you look at the handbook, the solution it takes about a couple of pages to complete the expression for the solution. So it is a nasty equation that provides the solution, very complicated. Fortunately, if you notice a special characteristic of this equation, you'll be able to solve it very easily. Okay? What is that? Well, we note that there are only even powers. We have the fourth power, the second power, and of course the constant term. There's no third and first power. Okay? So, if we consider instead of omega the unknown, omega squared as the unknown, you end up with a quadratic equation. Okay? So we solve this fourth order differential equation. I'm sorry, not differential, just equation, algebraic equation for omega squared, not for omega. And then you will get, if you solve it, two solutions. And the squares, then these are the squares of the solutions that you want to find. Okay? So you find omega 1 squared, omega 2 squared, and then you take the square roots to find the solutions to this equation. So the square roots, if you take square roots of this, you have 4 roots, which are plus and minus omega 1 and plus and minus omega 2. Now, frequencies of oscillation cannot be negative, so we discard the negative solutions and you just get the positive solutions. So consider 2 positive roots only. Okay, and these are omega 1 and omega 2. And these are the natural frequencies. Natural frequencies. So if you have a 2-degree of freedom system, let's say a system with 2 masses that are, the first one is suspended from the ceiling with a spring, and the second one is connected to the first with a spring. So if you consider these masses, then you have a system that oscillates in 2 frequencies. These are the 2 natural frequencies. Okay? So if there is a free vibration, it will oscillate into these 2 frequencies. Okay. The roots of the equation of motion are A1, B1, okay, and then times e to the j omega 1t, and there's a second root, A2, B2, e j omega 2t. Okay. The vectors A1, B1, and A2, B2 are the eigenvectors of a matrix. So A1, B1, and A2, B2 are eigenvectors of matrix M inverse times K Okay, these are the eigenvectors, and these vectors are called mode shapes. So AI, BI, this is a mode shape. And this is, there are two mode shapes in this example where we have a 2-degree of freedom system. Now, the eigenvectors are not unique. If you scale the eigenvector, let's say the eigenvector is 1 and 2. A vector with 1, the first element is 1, the second is 2. If you scale it by a constant, it's still an eigenvector. It satisfies the equations. So eigenvectors are not unique. That means if A1, B1 is an eigenvector, and so 2 times this vector, so 2A1, 2B1, 3A1, 3B1, and so on. Okay, so you can define the eigenvector only up to a constant. Now, in order to have uniqueness in this course, we'll consider that the first element is 1, okay? That is not the only assumption that you can make to solve the free vibration problem. You could consider that the length of this vector, the square root of the sum of the squares is 1. That's an alternative. So, but in this course, we consider that the first element is 1. In this course, consider eigenvectors with the first element equal to 1. Okay? How do we find the eigenvectors? Well, the first step is to find the natural frequencies. The first step is to solve this characteristic equation to find the natural frequencies. Once you have the natural frequencies, then you can solve this equation. The stiffness matrix minus the mass matrix scaled by omega squared AD equal to 0. So this is the equation that you solve. And if you put in this equation the first natural frequency, you'll get the first eigenvector. If you use the second natural frequency, you get the second eigenvector. Okay, so if you use omega 1, then you get the first eigenvector, which is denoted by A1, B1. And for the second frequency, if you put in the characteristic equation omega 2, then you'll be able to get the second eigenvector, which is A2, B2. Okay, once you have the eigenvectors and the eigenvalues, you can write the equation of motion, the equation for the displacement of the two degrees of freedom. Okay. So we'll write an equation for a vector which contains the two displacements. So general solution of equation of motion. The displacement x of t is C1 times the first eigenvector Ej omega 1t plus C2 A2 B2 Ej omega t 2 omega 2t. Okay, and this is also written as C1 times the first eigenvector V1 times Ej1t plus C2 V2, the second eigenvector, times Ej omega 2t. C1 and C2, these constants are complex. C1 and C2 are complex. And they get the form Ci, but the index I can be 1 or 2. The length of Ci, of this complex number, times Ej psi I. Okay. Now, we have said before that when we write equations that involve complex numbers, we mean that the equation is satisfied for the real parts. The imaginary parts are not important. So in the real form, the equation is as follows for the displacement. Real form x of t is a constant C1 times V1, the first eigenvector, times cosine omega 1t minus psi 1 plus the magnitude of this complex number, which is this, C2 times the phase angle phi2 cosine omega 2t minus an angle, phase angle psi 2. Okay, so let's summarize what we have concluded from this free vibration analysis of a system with multiple degrees of freedom. Okay, conclusions. First, if you have a system with 2 degrees of freedom or many degrees of freedom, say 2 masses, the first one is suspended from the ceiling and the second one is suspended from the upper mass, then the motion is the superposition of 2 harmonic or sinusoidal motions. The 2 have different frequencies. So the first conclusion is that the motion of the system is the superposition of 2 harmonic motions or waves. Harmonic motions, or modes. Okay, so you can write this kind of equation, vibration of system, is the first mode, mode 1, times a constant constant 1 plus mode 2 times another constant, constant 2. And if you want to make it more mathematical, you have this expression, the magnitude of this complex number C1 times the vector whose elements are the displacements of the 2 masses for the first pattern or mode times cosine omega 1 t minus phase angle sine 1 plus C2 phi 2 cosine omega 2t minus psi 2. Okay, so for a 2 degree of freedom system, you have one sinusoidal component at this frequency and another sinusoidal component at the second natural frequency omega 2. We have constants C1 and C2, and we also have these modes which give you the relative displacement of each mass for each frequency. Okay. Now, there are in this expression some numbers that are not defined. Even if you solve the free vibration problem, you still have some constants to find. The constants that need to be found are the two coefficients, C1 and C2, and the phase angles. In order to find the four numbers, you need initial conditions, two initial displacements and two initial velocities. Okay? The participation or contribution of each mode depends on the initial conditions. Okay, so this is the second conclusion. The third one is that the response of each mass is the superposition of two harmonic motions. Of two sinusoids. Sinusoid and harmonic is the same. With frequencies equal to the natural frequencies of the system. Okay. Let's see an example. Let's say that you solved the free vibration problem. You found the natural frequencies, the mode shapes, and also the phase angles psi and psi1 and psi2. These two. So we have C1, C2, we have psi1, psi2, we have omegas, and we have also the mode shapes. So let the first natural frequency be 1 radian per second. The phase angle of the first mode is 0. Okay, which means that there is a cosine wave, and it's just a pure cosine. And the first mode shape is a vector with ones, which means that in the first pattern of motion, both masses oscillate and they have the same amplitude. The amplitude is 1, and they oscillate in sync. The second natural frequency is lower, it's 1/2 radian per second. The second mode shape is, the phase angle, the second phase angle is 0, 2, and phi 2 is 1 minus 1. Okay? This is a kind of a fictitious example. Now, what can we tell about the motion of the system? Well, the motion of the system is the superposition of two harmonic motions in two frequencies. So let's see the first one for frequency 1 radian per second. Okay, so frequency omega 1 equal to 1 radian per second. This is the displacement of the first mass, and this is the displacement of the second. Since we have a cosine, then we have this type of motion. The cosine starts from 1 at time equal to 0. Okay? And the second one, since the amplitudes are the same, the phase angles are both 0, it's the same, it's a copy of this motion of the first mass. So just to draw it, I will mark this point where we have a 0 displacement. So you have exactly the same displacement. Okay. So this is the first mode of vibration. First mode of vibration. Okay, so if you were looking at the masses, the way that the masses move in the first mode, they move like this. Okay. In the second mode, the frequency is 1/2. That means it takes longer to complete one cycle. The phase angle is 0, which means that you still start from 1. But then the mode shape has two elements, 1 and -1. And that means that when one mass moves up by 1, the other moves in the opposite direction. So the masses move like this. This is the pattern that you will see. So let's see the mode shapes. I'm sorry, the pattern of motion. Frequency omega 2 equal to 1/2 radian per second. X1 of t. This is the axis, time axis. Now, since the frequency is 1/2, it takes twice as long to complete one vibration cycle. So you have something that oscillates at a slower rate, something like this. Okay. This is omega 2 equal to 1/2 radian per second. Now, because the two displacements are opposite when the first mass has displacement +1, the second has -1. So you have something like this, a displacement like this. So this is x2 of t, and this is -1. So in the second mode, the masses move up and down like this. Okay, this is a good point to stop. So we'll continue with next time with an example and understand the motion of systems and systems with multiple degrees of freedom. Now, before we complete the presentation, the lecture, I want to say something about the motivation, why we study the mode shapes and natural frequencies. The reason is that most systems vibrate in the first few modes. Although a very complex system, say a system that has 1,000,000 degrees of freedom, that's extremely complicated system. A building or a car may have 1,000,000 degrees of freedom. That means there are 1,000,000 mode shapes. However, only few, the first few, say the first 10, may be excited. The remaining modes are not excited. So the system actually oscillates, say, in the first 10 modes. And using this kind of modes, you can replace this complex system with 1,000,000 degrees of freedom with one that has only 10 degrees of freedom. And that makes our lives much simpler. So that is one of the motivations for considering mode shapes. If you know the mode shapes of a system, and you know that few, the first few are excited, then it's very easy to perform vibration analysis and simplify the problem a lot. So this is why it's important to understand about mode shapes. So let's stop here and we'll continue with an example and complete the free vibration analysis next time.